Hello everyone, this is the pre-recorded videos for Chapter 5, Homework 4. I'm going to go over a couple problems starting with this one, 5.5. So we're given this circuit, it's an RC circuit, we're given the voltage, we have a resistor and a capacitor. We're given the voltage across the resistor, VR, and we're given VC, the voltage across the capacitor. The first part of this asks us to write this in rectangular form. Write VR and VC in rectangular form. So the same way we went over in class on Monday, we will convert this from polar form to rectangular form. And we do this by finding the real term using cosine and the imaginary term using sine. So we have, for VR, we have 9.5. Sorry about this. It's the first time I'm using this right pad, so it takes a little getting used to. So 9.5 times the cosine of 18.44 plus j times 9.5 times the sine of 18.44. And this comes out to equal 9 plus j times 3. And this is rectangular form. Now, next we want to do is find VC in rectangular form. And the same way we did it with VR, we're going to do it with VC, just with different values. So we have 3.16 times the cosine of negative 77 cosine of negative 71.56 plus j times 3.16 times the sine of negative 71.56. So this comes out to equal 1 minus 3j, j times 3. And this is also rectangular form. The next part of this asks us to find find V, which is equal to VR plus VC, and they want that in both rectangular and polar form. So if we're adding, the easiest way to do it is to add in the rectangular form. So let's write B, and we want V equal to V of R plus V of C. So we then can rewrite this as 9 plus 3j plus 1 minus 3j, or j3. J times 3. Now, looking at this, we know that the imaginary terms, which are the j terms, will cancel, and we're left with just a real component, which is 10. So we have 10 minus 0j volts equal to V. Now we want to convert this to polar form. We do this by finding the magnitude of V and the phase of V, or the angle of V. So you find the magnitude by doing the square root of the real times the real squared plus the imaginary squared. But there isn't an imaginary component, so it's just the real squared, the square root of that, which is equal to 10. And because if we come back to the real and imaginary axis, that's imaginary, this is real, because there's no imaginary term, this is only going to lie along the real. I'll do a different color for this. So it's only going to lie along the real axis. So we have 0 degrees as our angle. 0 degrees. So we can now represent this as V equal to 10 at an angle of 0 degrees. This is our polar form, and this is our rectangular form. And there's a third part for C, or for 5.5, which is C. And C asks us to find the real and imaginary parts of V. Well, we did that if we look at it in rectangular form. And the rectangular form of V is equal to 10 minus 0j. So the real part is equal to 10, and our imaginary part, which is our j term, is equal to 0. And that's all that it asks for part 3, or C. So that's all of 5.5. The next problem that I want to do is 5.12. So 5.12 is another, let's do 5.12. So 5.12, and we're given another circuit. This time it's a current, not a voltage. That's a capacitor. That's a poorly drawn capacitor. That's capacitor. This is a resistor. And now that's R, that's C, and right here we have a current IC. This is a current I, and this is a current IR. And now we're given IR equals 0.929 at an angle of minus 21.8 degrees. And then we have IC, which equals 0.37 at an angle of 68.2 degrees. And then, similar to what we did before, it wants us to write them in rectangular form. And then it wants us to find I and do the imaginary real parts. So let's go to the next page, and I'll rewrite IR and IC. So IR is equal to 0.929 at an angle of minus 21.8. IC is equal to 0.37 at an angle of 68.2. And this is in amps. Both of these values are amps. So if we want to find IC, this is the polar form. And we want to find rectangular. We find rectangular by doing the sine and cosine values. So the magnitude times the cosine of the angle for the real term, the magnitude times j sine the angle for the imaginary term. So let's do that. So we have 0.929 times the cosine of minus 21.8 plus j times the sine, times 9.929 sine of minus 21.8 degrees. This comes out to be 0.863 for the real term minus j of 0.345 for the imaginary. term. This is an Ames, and that was IR. Now IC, we do the same exact method. So we have 0.37 times the cosine of minus 68, no, positive 68, 68.2. So 68.2 plus J times 0.37 times the sine of 68.2. This comes out to equal 0.137 plus J times 0.345. And this is also in Ames. So this term is the rectangular form for I of R, and this is the rectangular form for I of C. And this was what part A wanted us to find. Now, for part B, it asks us to find I. So I is equal to IR plus IC. And if we're adding the terms, the easiest way to add them is in rectangular form. So we'll rewrite our rectangular forms and we will add them together. So we have 0.863 minus J times 0.345 plus 0.137 plus J times 0.345. And similar to the last problem, the J terms or the imaginary terms will cancel, and we're left with I equal to 0.863 plus 0.137, which equals 1. So we don't have an imaginary portion of this. The imaginary portion cancels out. We have just a real term. So the rectangular form of this is 0j. 1 plus 0j. And then I in polar form wants us to find a magnitude, which is done by 1, the real term squared plus the imaginary term squared. We don't have an imaginary term, so it's just the real term squared, the square root of that, which is equal to 1. And similar as before, if we don't have any value in the imaginary term, our angle is going to equal 0. So we can rewrite I now as 1 at an angle of 0 degrees. And this is our polar form. This is the rectangular form right here. This is the polar form. Now, C then asks for the real and imaginary parts. We've already done that. So the real part is equal to 1, and the imaginary part is equal to 0. And we can find that from we can easily see that from the rectangular form right here. Alright guys, I hope this video was helpful. Any questions, just ask me in recitation or shoot me an email. I'll see you.